The purpose of this video is to show you how the builder or team supporting a race car would find the center of gravity of that car. Of course, it would work on any car. We'll illustrate weighing the car in two different positions, then computing where the center of gravity is based on the weight shift between the first and second positions. It's really quite a simple matter to weigh the car flat and compute a location of a vertical line with the CG somewhere on that line. That line, in math teacher terms, is the set of all points where the center of gravity might be. So we'll need another line. We're dealing with gravity here, and gravity only knows how to go straight up and down. So we'll need to tip the car, get a second vertical line, and then do a little trigonometry to figure out where these two lines cross. This intersection is the location of the center of gravity. So let's talk about that simple matter to find the vertical line. We can prove with a simple analysis in the study of statics that if, say, 60% of the car's weight is on the front axle, then the distance from the rear axle, yes, the rear axle, to the vertical line containing the center of gravity is 60% of the wheelbase. This makes intuitive sense because the heavier axle must be closer to the CG than the lighter axle. So let's put some numbers on that. Let's say our car's weight distribution is 60-40 front rear, or 60% of the car's weight is on the front axle. This is not atypical of larger American cars. Many are much worse. In our example, the wheelbase of the car is 300 centimeters and the total weight is 1,000 kilograms. If we look at our scales, then we'll see that there's 600 kilograms on the front axle, 400 kilograms on the rear axle. So the front axle is carrying 60% of the weight. Our vertical line then must be 60% of the wheelbase, or 300 centimeters times 60% times 0.6. That equals 180 centimeters forward of the rear axle. So that is where we draw our vertical line. Now we have to tip the car. It's much the same, but a little trickier. We're going to do the same math, but we can't use the wheelbase of the car anymore because that won't be level. It'll be tipped up in the sky somewhere. We'll have to use the horizontal distance between the axles and compute our vertical line from that. To compute the horizontal distance, we'll need to use a simple trig function. The wheelbase times the cosine of the tip angle is the number we'll need. In this case, the tip angle is 20 degrees. So the horizontal distance between the axles is 300 times the cosine of 20 degrees, and that equals 281.908 centimeters. But the weights aren't going to be 60-40 anymore. With the tip back, some weight will come off the front axle, and that weight will end up on the rear axle. So let's say this time the weights come in at 550 front, 450 rear, or 55-45 front to rear. Now we'll need to draw our horizontal line forward of the rear axle 55% of the way forward horizontally. So the number we're after here is the 281.908, which is the horizontal distance between the wheels, times 55%, and that computes to be 155.05 centimeters. And as I've explained previously, where these two lines cross is two lines, which are the set of all points where the CG might be. And where those two lines cross, we narrow it down to 1 point, and that's where the center of gravity is to be found. Now, you can see that we've got ourselves a geometry and trigonometry problem to solve here to actually put dimensions on where the point is. More accurately, we need to find the height or the up and down position because we already know the end position from the very first step. So at this point, I'm going to start with a different car and go through it step by step with actual numbers and until we've developed the equation that tells us where the CG actually is. Okay, so here's the car we're actually going to do all the work on. So where do we start? We need to measure the wheelbase or look it up if this is a production car. This new car now has a 300 centimeter wheelbase. We need to flat weigh the car, and when we do, we find that our front scales read 550 kilograms at the front and 450 kilograms at the rear. So we know that our front rear weight distribution is 550 of 1,000, or 55% on the front axle, 45% on the rear, and we can calculate the location of our vertical line using the front weight as a percentage of the total weight to compute the distance forward from the rear wheel as a percentage of the wheelbase. Okay, so here we go. It's 55% of the wheelbase, or 0.55 times 300. That means our vertical line is 165 centimeters forward of the rear axle. That's how you get that location, and here's your equation. I'll just leave that up there for a few seconds so you can ponder it. So that was the easy part. Now we're going to tip the car up 20 degrees and come up with our second vertical line. We'll bring the first vertical line along for the ride here. You can see where it is. But with the car tipped, the weights at the front and rear axle change. In this case, we'll find that the axle weights are now 465 kilograms on the front, 535 on the rear, or 46.5 front, 53.5 rear. So let's find our horizontal distance, and use the ratio of the front weight to the total weight to find the distance forward along the horizontal line, and we'll draw our vertical line right there. Our horizontal distance between the axles, as before, is the wheelbase times the cosine of the tip angle, which works out in this case to be 281.908 centimeters. Using the front axle weight of 46.5% of the total weight, we strike our vertical line at 0.465 times 281.908 equal to 131.087. Now remember, when we flat weight it, we got this 165 centimeter dimension. We already know that the longitudinal location of the CG is there from having done the flat weight. All we need now is the vertical dimension. And at this point, we've rounded up enough geometry that we're within reach of our little trigonometry problem. Okay, so we need this leg, which I'll call I. We can find I if we know J, but we don't. We can find J if we know K, but we don't. But we know L, and that will get us K. So using cosine function, we find that L over cosine 20 is K, and the value of that is 139.5. We know that J plus K is 165. That came from our flat weight step. So now we can find J as 25.5 centimeter. We know the tilt angle is 20 degrees. So from simple right angle trig, we can find I. I is equal to 25.5 over tangent 20. That would give us 70.06 centimeters. And that, in fact, is the vertical location of our CG from the axle center lines. If you want the CG height from the ground, just add one wheel radius. So that's our final answer. The location of the CG is 165 centimeters ahead of the rear axle and 70 centimeters above the axle center lines. But I promised you an equation, so let's develop that. First, we need to gather all of the parameters that could make one car different from another and give them each a name. I like single letter variables for simple systems like this. So those 5 parameters are going to be A through E in order: the wheelbase, 300 centimeters, the total weight, 1,000 kilograms, the tip or the slant angle, 20 degrees, the front axle weight when the car is flat, 550 kilograms, and the front axle weight when the car is tipped up to 20 degrees, that would be 465 kilograms. Now we'll name all of the lengths that we need to include in our calculations from this drawing, and then we'll walk through it like we did a minute ago. H will be the horizontal location of the CG, and I will be the vertical. Now we can work these equations individually in this order, just punching the numbers into a calculator. H is the horizontal answer. From there, we work our way down to I, which is the vertical answer. If that works, then we're on the right track and we can begin the process of combining the equations until we have a single equation with only parameters A through E, which are given to us, in it. Doing just that gives us the correct results. So now it's time to combine and simplify. The simplification process looks like this. you can see that parameter m has only a and c in it. But L has a parameter m, which isn't one of our given factors a through e. So if we plug the m equation, a cosine c, into the L equation, then we have an equation for L that contains only a through e values. Continue this process in a similar vein until you've eliminated all of the h through m variables. In the process of working through this, a few things fall out along the way, and you end up with this oh so elegant pair of formulas. All you have to do is collect the data on the car, plug in the 5 measurements of length and weight, and you've got the horizontal component from the first equation and the vertical component from the second equation. Don't forget that the vertical one is measured from the axles, not the ground, so if you need the CG height from the ground, add in the radius of the wheels. Okay, so we've slogged through it this far. Let's try out our formulas and see if we get 165 for the horizontal and 70 for the vertical. We'll just plug in the values we know and see what we get. So there we are. And what do you know, through the wonder of mathematics, we've actually got the correct answer. Here's a little summary page for your viewing pleasure. Remember that you can substitute raised axle weight or lifted axle weight for front axle weight. If you want to lift the rear end, just keep in mind that the H values will come from the low end. Don't forget to like and subscribe. Thanks.